Hello and welcome back. Today I want to start talking about power supplies and the various parameters that characterize their performance. In general, the choice of power supply is done taking multiple factors into consideration. There is a reason why a good datasheet has multiple pages with tables and numbers and graphs. Now, the parameter I want to focus on today is the static output voltage accuracy. What is the output voltage that you should actually expect from your power supply? So, if you're curious, then keep watching. So, to start things off, static conditions refer to having a fixed input supply voltage and a fixed output load. These can of course be varied, but the supply is given enough time so that the voltages and currents end up stabilizing and having a fixed value. So what is there to say? I mean, if you need a 5-volt power supply, you get a 5-volt power supply, right? Well, no power supply will give exactly 5 volts, or any other value for that matter. There is always a tolerance or a deviation, and the voltage at the power supply output is not necessarily the voltage that arrives at the load. So regardless of power supply type, whether it's a linear or switching regulator, there are quite a few common elements which impact the output voltage. Another thing to mention is that the supply has a normal operating range to get the expected output. Otherwise the circuit won't work. Either it will not be able to operate correctly or it will get destroyed. Now, for today's discussions, I will consider the circuits to be kept within their normal operating range. Now, to understand why the output may not be exactly the value that you expect, we first need to look at how a power supply measures and adjusts its output voltage. So there will always be an input voltage, and there will always be some sort of regulating circuit. This may be as simple as a series transistor or as complex as a switching circuit. And then this is connected to the final load. Now, commonly the amount of current that is allowed to pass is controlled by a bit of analog circuitry. So you will have a voltage reference, a sensing circuit commonly built with a couple of resistors, and an error amplifier that compares the two values and based on the result drives the regulating circuit. So this basic control loop is built in a way that if the output voltage is lower than the desired value, more current is allowed to pass, and if there is too high of an output voltage, then less current is allowed to pass. And when the circuit is in a static stable point, the voltage after the resistor divider is approximately equal to the value of the reference voltage. Depending on how the power supply is built, more or less of this analog circuitry can be integrated or can be implemented discretely and separately. So if we consider a fixed voltage output circuit like the LM7A series, the entire circuitry is contained inside of the IC. So your sensing circuit, the voltage reference and the comparator and everything else is inside of a single integrated package. This will make the output of a fixed value. However, other circuits that offer variable outputs, like a power supply built around the TL431, has the voltage reference and comparator integrated, and then the sensing resistors are placed outside, so the user can put whatever values they want here. Now, a power supply may be split into more bits than this, but these are the two most common approaches when analog control is implemented. Specifically, the feedback resistors may or may not be integrated. Now, most power supply datasheets, like this one for the LM323, will give an indication of the output voltage range under some specific test conditions, which keep the circuit in its normal operating range. So you will have an initial tolerance in the internal circuitry, and then by varying the various parameters, the total output voltage will end up having a slightly larger variation. So things like supply voltage, output current, and even temperature will have an impact on the exact output voltage that you're getting. Now, depending on the exact circuit that you are using, you can have better or worse tolerances. So the LM323N has about plus minus 4% of tolerance, but the A version already has a much tighter plus minus 1%. So based on your use case, you need to look for a supply that has a sufficiently tight tolerance. Now, if you're using exactly the implementation recommended by the manufacturer in their datasheet, you should get the results as presented in the datasheet. However, if you're using your own design, it's usually a good idea to verify the performance of your practical circuit. Because if there is a way to get things wrong, you might just be able to find it. Now, verifying the output accuracy can be done with relative ease, and to highlight this, I prepared the setup. So I have a test power supply from an older video, and to measure it, first of all you need to monitor the input and output voltage, and it's important to mention that the monitorization needs to be done at the supply terminal, so not somewhere on the line. The input needs to come from a variable power supply, so you can observe how it behaves with different input voltages. And then for the output, you need to monitor it through an ammeter and preferably connect it to a variable load, so you can observe the supply with different load values. As a bonus, if this is of concern, the supply can be kept in a thermally controlled environment to observe its behavior in extreme temperatures. And finally, this measurement needs to be carried out in all extreme case combinations, so maximum and minimum input supply, maximum minimum load, maximum minimum temperature, and usually a typical use case. And as an example, using this setup for this particular board, I got this set of results. Now, the reason why the output may not be the exact value that you expect is because the control circuit is not built from perfect components. So the feedback resistors will have a clear initial tolerance, the voltage reference has a specific tolerance and a drift in time, the error amplifier has an input offset as well as a drift, and while all components and circuit bits are temperature dependent. So the various elements in the circuit will have a specific effect on the output accuracy, and the total accuracy can be calculated based on all of these effects combined. So the main contributors to output voltage accuracy are the elements present in the control loop responsible for setting the output voltage. Not much can be done about the parts that are integrated, but you may be able to influence things though when these components are external. So based on your application needs, a more or less precise regulator may be required to start off with, and then the only way in which you have some control over the output value for a given regulator is when you can influence the external sensing circuitry. Here there are two big things to consider: the resistor divider itself and the exact measurement point. So part of the output voltage tolerance will be impacted by the resistor tolerances. So using 0.1% resistors will make a far more precise power supply than using 5% resistors, but at the same time, there's no point in investing in extreme precision resistors if the internal reference has a high tolerance. In the end, you need to consider the global tolerance of all of the supply elements combined. Now, the measurement point is also important to observe, since in the real world, the trace between the power supply and the load has a finite value of resistance. In other words, the higher the current that is pulled by the load, the lower the voltage that arrives. This will apply regardless of whether the sensing is built into an integrated circuit or is external, and is independent of the initial component tolerances. If we now come back to our experimental setup and change things a bit, so what I did here, I kept the voltmeter that measures the output directly on the power supply output, but the second voltmeter is measuring the voltage at the load, and while the ammeter stayed in the circuit to measure the current consumed. So what we can see is that at very small load values, the voltage at the supply output and the voltage reaching the load is more or less the same, so any difference is quite small and negligible usually. However, if current gets increased, so we go up to 1 ampere, we can see a very clear difference between what is at the power supply output and what reaches the load. So there's about 270 millivolts of voltage difference. Now this difference is proportional to the current that's being pulled by the load and the equivalent resistance of the wires. So the connectors between the power supply output and the load, both positive and negative lines together. So if we know this resistance and we know the current draw, then we can work out what the voltage drop will end up being. Now, whether this difference is an actual problem, that depends on the application. So you need to know exactly what is the voltage that you need at your load at the maximum current draw. When designing the layout for a power supply, a huge impact, either positive or negative, in output voltage accuracy can be achieved based on the exact measurement or sensing point. Where is the voltage that the supply is regulating? And more importantly, where is the load that is being supplied? First common practice to mention is the output voltage that is being measured at the output capacitor. So what I have here is a datasheet for a switching converter, so the LM25085, and although you can measure the voltage anywhere on the output net, so anywhere between the inductor and the output capacitor, it's a common practice to connect your resistor as close as possible to the capacitor rather than the inductor to minimize the amount of noise. So in the actual board that I ended up making, even though the entire output voltage net is quite large, the measurement resistor is connected close to the first output capacitor. So by applying this method, you're preventing less of the noise coming from the inductor to get pushed into the feedback line and the more filtered DC value to be sensed. Now, for relatively low current applications and short distances, this is almost always the approach that is taken. But as we saw with our experiments, where a similar principle is applied, this will not guarantee a precise voltage at the load if it's far away from the supply. Next best thing is remote sensing. Rather than regulating the voltage at the output of the power supply, you can look at the voltage that reaches the load and regulate that. Now, this will not always be a possibility based on how the power supply is built, and you can only regulate one point, so it won't really work with multiple loads connected to the same net. However, it's a common feature present in higher-end benchtop supplies or with high-current PCB-based supplies. Now, there are two main ways in which you can do this. First, you can only measure the regulated line by extending the measurement wire all the way to the load. In practice, you might also have some extra components close to the power supply to filter out noise and ensure stability, but the idea here is to regulate the average voltage that is present at the load. This approach has, of course, the disadvantage that the reference ground line can still provide some amount of voltage offset. But regardless, this is better than the direct measurement at the power supply output. The next best thing is to measure both lines at the load. So this will most often be applied when the power supply has dedicated pins for this, and you only want to use these extra lines for sensing. All of the high current needs to run to the supply over different lines. So you will have a dedicated high current positive line and a dedicated high current negative line. This approach ensures maximum accuracy and is usually used when even small voltage differences that could occur would lead to unwanted issues. So normally with very high currents or when the distances are very long. Another thing to keep in mind are ground offsets within the regulator. A poor layout may allow a voltage potential difference to occur under high current conditions, which will impact the final output value. The thing to keep in mind here is that even in short distances, you can still get voltage difference caused by high currents running through the ground. So the error amplifier does not necessarily compare the voltage reference voltage and the resistor divider voltage, but rather it compares these voltages plus whatever ground offsets occur in between these points and the amplifier's ground connection. And because of this, rather than having the ideal case where the output voltage is equal to the reference voltage times the resistor ratio, in reality the output will be equal to the reference voltage minus the ground offset in between the 2 points times the resistor ratio. One workaround found in older schematics, or when discrete implementations are used, is to have all of the sensitive circuitry connected into a single ground point at the output of the power supply. So to have a ground start point which will not allow any sort of voltage differences to occur between the various important circuit bits. In more modern times, this problem has become even more stringent, specifically in things like switching converters, where you can have very high currents with very fast transitions because of the switching circuitry. And this can cause large potential differences. So one method applied is to perform a ground separation, where the power stage and the transistor driver are connected to one ground, which is the power ground, and then the error amplifier, reference, measurement circuitry, and well, any other sensitive bits are connected to a analog ground. And the two grounds are interconnected in a single point where there is very little noise. Now, different implementations of this principle exist, but the idea is to keep any noise or potential offsets from interfering with the supply's analog or sensitive bits. In the end, to get a precise output voltage from a power supply under static conditions, you need to keep multiple factors under consideration. First of all, you need a power supply with a precise and stable internal construction. Then you need to have precise feedback resistors if these are external. And finally, the power supply can only regulate the voltage in the point that it's sensing. So the exact location of the measurement will be the point where the voltage is closest to the value that the power supply should be outputting. Now, keeping the output precise under static conditions is one thing. What about dynamic conditions? Well, that's a topic for next time. For now, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye.